All right, so we want to model this oscillator with friction present. Okay, so mass times acceleration of this guy. The forces on, so we'll look at all the forces. What Mr. Newton says, mass times acceleration of the object is equal to the net force on the object. Here's the spring force minus kx, and here's the friction force. Okay, so m d square x by dt square is minus kx, and velocity of this object is dx by dt. Okay, and we'll bring this term on the side, m d square x by dt square plus b dx by dt plus kx equal to 0. Okay, so let me go to my, let me show you one thing. Yeah. All right, so what we saw was m d square x by dt square equal to minus kx minus b times dx by dt. M d square x by dt square plus kx plus, well, what I want to do is write the dx by dt plus kx is equal to 0. So, and we'll divide by m, so d square x by dt square plus b over m dx by dt plus k over m x equal to 0. And k over m was equal to omega square. We had defined it as omega square. So d square x by dt square plus b over m dx by dt plus omega square x equal to 0. So without friction, our differential equation was d square x by dt square plus omega square x equal to 0. So with friction present, it's become slightly more complicated. You have this extra term. Okay, so now you'll be solving a slightly more complicated differential equation. But here's the good news: you learn to solve this harder problem, and the solution to this harder, simpler problem is contained in it. If you want the solution to this problem, all you do is put b equal to 0, and you get that solution. Okay, so now what has happened is, so here is this extra term when you want to account for friction. Okay, so that's what we're doing. All right, and again, so this differential equation has a second order derivative, and it has a first order derivative. Okay, again, it's a linear differential equation. All right, so there is the differential equation, there is the friction term. And when you want to go to the frictionless system, you just put b equal to 0. Okay. All right, and here is the solution to that differential equation. Okay, so again, you see it's the same old equation, except that now the amplitude is decreasing exponentially. Okay, so and that's what you saw there. So you see the amplitude was decreasing exponentially, and that's what's written there. So amplitude times this exponentially decreasing factor. Okay, so there was the solution to that differential equation. Again, now what we have learned is in just 20 minutes, we have learned to model a more complicated system. We started off modeling a system where there was no friction, and now we've learned how to model with friction present. And here's the solution. Okay, and you can see that the oscillation frequency is slightly altered. This was the frequency this would have been the frequency without friction, and with friction present, the frequency got altered a little. All right, so like we said, the amount of friction determines the kind of oscillations that you have. If there's little friction, you'll have a system that will oscillate, and the oscillations will die after a long time. Okay, if so, here's a system which doesn't even oscillate; it just goes back to its original position, equilibrium position, and that happens when B plus B by 2m equal to omega naught, which omega naught being square root of k by m. Okay, so when this term is 0, then that system is called critically damped and it doesn't oscillate. And if this term were bigger than that, this becomes an imaginary number, and the system doesn't even go back to its original equilibrium position. Okay. So in systems like this, when you hit a pothole, what you want to do is you want to make sure that your wheel comes back to its original shape, location. You don't want it not over damped, and then the wheel would not come back at all. And this would, you want to be slightly under critically damped, okay, and you don't want too many oscillations. So you would design your systems like so. All right, so this is an underdamped system, this is a critically damped system, and this is an overdamped system. Now we'll take one step further. Okay, now we'll apply an external force. Okay, so this is so imagine a child on a swing. You get this child swinging, and then if you let go, because of friction, the oscillations will slowly start dying down, and the child will start crying. And the way to make the child quiet is you start pushing again. Okay, so that is, you're forcing the system externally. So we'll look at forced oscillations. Yeah. So if there is friction, it's possible to compensate for loss of energy in a damped system by applying an external force. Okay. And so this will bring us to resonance in a little bit. Okay. So here's the net force on the system. Here's the applied force, the external force. You're pushing. And so here, what we're going to model is a sinusoidal force. So F naught sine, the subscript D telling you it's a driving force, the driven frequency. Here's the friction force. Here's the spring force. And so this is the net force in the system, and that's equal to mass times acceleration of the system. Okay, there are two frequencies here. This is the natural frequency. Okay, so let me go to my, okay, so. All right, let's add a page below. Okay, so in that equation, so force, this was the amplitude of the force, cosine. Okay. This was the friction force minus kx plus m was equal to m d square x by dt square. Okay, and so the solution xt was a omega d omega cosine. Okay, so so our solution, this is the driven frequency, this is the natural frequency of oscillation. which was K over M. Okay, and this was the frequency, the forcing frequency. Okay, so the system is oscillating at the force frequency. Okay, but we'll see that when the driving frequency matches the natural frequency of the system, bad things can happen, and that is resonance. Okay, so we'll talk about that. So when the driving frequency matches the natural frequency, then okay, and bad things can happen, and so we'll look at that. Okay. All right. So the oscillator vibrates at the driving frequency omega d. Omega is the natural frequency of the oscillator. So here's the amplitude. This amplitude, which is a function of both the driving frequency and the natural frequency. So here's the amplitude. This is the amplitude of the force, applied force, external force divided mass. And you see this is the driving frequency, and that's the natural frequency plus the friction term. So let's say the friction term is small. If the friction term is small and this driving frequency matches the natural frequency, the denominator will become small and the amplitude can become large. Okay. Okay. So the amplitude can become large, meaning, well, the object will oscillate with large amplitude oscillations, and that can compromise structures. Okay. So you see what this graph is showing you is as the driving frequency matches the natural frequency, you see as this becomes close to 1, the amplitude is increasing. Okay, for a given, so this is given damping. So for this damping, as the driving frequency matched the natural frequency, the amplitude became large. And what this is showing you is if the damping is small, this amplitude can get super large. Okay, and you can compromise structures. Okay, you can break down structures. So actually, let me show you a simulation. Okay, so let's let's look at a video. And, everybody needs to see this video. It's taken a physics course. Yeah, there you go. Okay, so this was a bridge built near Seattle. Okay, so here we go. This was.
Wind provided the energy to set the 1940 Tacoma Narrows Bridge in motion. Oscillations traveled through the center span and reflected from the support towers. By the principle of superposition, the primary and reflected waves turned into a standing torsional wave. A node provided the safest path for one man's escape from the bridge. Vortices of air turbulence modeled here by investigators broke away from the bridge at a frequency that closely matched the natural frequency of the second harmonic of the center span. Every time a vortex split away, the bridge was pulled slightly. Resonance developed, and the amplitude of the standing wave grew and grew until waves ripped the bridge apart.
Okay, so what you saw was when the driving frequency there, the driving frequency, so what was happening was, okay, so let's go back here. Okay, so here's a top view of this thing. This is land. So this is the bridge. So this is land. And these are the piers underneath the bridge. And the wind was blowing like that. And vortices would break away at a frequency. So every time they broke away, they're pulling on the bridge. Okay, so you are exerting an external force on the bridge. That was and the frequency at which the vortices broke away matched the natural frequency of a bridge, the second harmonic of the bridge. That's what the video was telling you. And when this happened, you see the amplitude increased. Okay, so when the driving frequency matched the natural frequency, and this term was small for the bridge. You set up large amplitude oscillations, and you see that compromised the structure and the bridge collapsed. So after that experience, we learned to make this B large. We learned to make the damping constant large, and you see as you make the damping constant large, the maximum amplitude is decreased, and that was the idea. Okay. So that was a hard lesson learned. Okay, so let me show you. So when the frequency of the driving force is near the natural frequency, the amplitude of oscillation can be large. The dramatic increase in amplitude is called resonance. And so the amplitude increases with decreased damping. So with damping small, the amplitude of oscillation will increase. Okay, I want to show you this simulation. We'll come to that in a second, but let me finish the slides and then we'll come to that. Okay, so here's a case that happened in Mexico City. The epicenter of the quake of 1985 on the western coast of Mexico was 400 kilometers from Mexico City. Angular frequencies of the seismic waves that reached Mexico City were concentrated around 3 radians per second, matching the natural frequency of intermediate buildings, which collapsed. Taller and shorter buildings survived. Okay. So now, well, these days we build a lot of tall buildings. So tall buildings are staples of a major city. The trend is to build taller, slimmer, and lighter structures. You're using less material and making them cheaper. So for instance, the World Trade Center, feet for feet, so elevation for elevation, use 30% the material of the Empire State Building. Okay, so that's the kind of savings that can be done. Okay, so however, because they're lighter, these structures are more prone to vibrations, which cause discomfort, and it can damage the structure and structural failure as well, unless you incorporate damping. So you don't want them to sway too much. By the way, the Burj Khalifa in Dubai sways 2 meters at the very top. 2 meters is over 6 feet. I guess so you have to incorporate those facts into the construction. So here's a building in Philadelphia, and here's how you can incorporate damping. So at the very top, that structure is filled with water, and as the building sways because of earthquakes, wind, and stuff like that, as the building sways, the water dampens the oscillation. Okay. All right. So before we quit, let me show you a simulation that is quite good, and actually we'll do a lab based on this simulation. All right. So, okay, so what we'll do is this. Okay, so we have 4 oscillators. This will be the driver. So imagine these are the children on swings, and this is you pushing. All right, so resonator 1, damping constant, okay. Okay, frequency of resonator 1 is all right. So frequency of resonator 1 is 1 hertz. Frequency of resonator 2 is 1.5 hertz. Frequency of resonator 3 is 2 hertz, and frequency of resonator 4 is 2.5 hertz. Okay. All right. So what we're going to do is 1, 1.5, 2, 2.5 hertz. Okay. So what we're going to do is we're going to change the frequency of the driver. So this is the driver frequency, 1 hertz. And you see this guy's frequency matches the natural frequency of this oscillator. And this guy is oscillating like crazy, and these guys are not there's not much going on here. I'm going to keep the driving amplitude the same. Okay, now I'm going to increase the frequency. Okay, so now you see this frequency doesn't match any of these frequencies, and none of them are oscillating with crazy amplitudes. Okay. Now let's go towards 1.5. Okay, so again 1.3, nothing drastic is happening. Okay, so imagine this is Earth, this is an earthquake, and the earthquake frequency is not matching the natural frequency of any of the buildings, and nothing drastic happens. None of them will collapse. Now this earthquake, this frequency matched the frequency of this guy. This guy is gone. This guy is history, and the other buildings will survive. Okay. And now let's go to 2 hertz. Okay, so you're getting, so now you're matching the natural frequency of this guy. And this is resonance, and you saw that in this Tacoma Narrows Bridge. When a driving frequency matches the natural frequency of one of the structures, disasters can happen. So you would want to build damping into the structure. Okay? The more damping there is, the smaller the oscillations will be. Okay. All right, that about covers all the topics from this lesson. Okay, and now